All right, good afternoon, everybody. Welcome back to Intro to Physics. Today is day 6, so we are moving along here. And we're going to just jump into where we left off yesterday. Let me go ahead and share my screen.
Hello, Miss Samora.
Hello.
How are you feeling today?
I am feeling a lot better. Thank you.
You're welcome.
Okay, so just really quickly, do you guys have any questions from the material from yesterday? Velocity time graphs and acceleration time graphs, and how those things are related to each other. It's a very similar process to what we were talking about last Thursday with the position time graphs, finding the slopes, those sorts of things. Okay, well, if you do have questions, if they come up today, again, feel free to ask. Now, it should have left off yesterday with a bonus problem. So I don't know if you got a chance to try this bonus problem on your own. But if not, just quickly take a look at this. We are going to run through the answer to this together to sort of review from yesterday. Okay, so for this give it a try problem, you were to sketch the velocity time graph and the acceleration time graph from this position time graph. All right, so we can clearly see that this graph is broken up into distinct segments, different sections that have different slopes. And remember, to go from a position time graph to a velocity time graph, we just take the slope of that particular section, and that is the velocity for that particular section, right? Once we have the velocity time graph, we can create our acceleration time graph in the same manner by taking the slopes of each segment.
All three of them are basically derivatives of each other. So the velocity graph is the derivative of the position graph, and the acceleration graph is the derivative of the velocity graph.
Yes, and if you've never taken calculus and you don't know really what a derivative means, that's actually the purpose of today, is to teach you derivatives and integrals. So we'll get into that in just a moment. Curious. Okay, so it looks like I don't have the slide in here that has the answer, so we'll just talk through it. Okay, so in this first section right here, we can see that it's a horizontal line, so the slope would be 0, meaning that for that portion we have a velocity of 0. This segment has a negative slope, so we could calculate the slope of this segment by doing rise over run. And in this case, our rise is negative, right? It's going downwards, so that would be a negative slope. So the rise of that would be -3 divided by that time interval. So from 2 seconds to 5 seconds would be 3 seconds. So -3 divided by 3 gives us a slope of -1. So on our velocity time graph, we would have -1 as our value from 2 seconds to 5 seconds. Right. Similar process for the other ones. This section is a positive slope, so we could find that by doing rise over run, get the value of that. That would be the value of our velocity graph at that point. And you keep going section by section and doing that same thing. Now, once we have our velocity time graph drawn, you should notice that each of those segments, even if they're at a different part along the y-axis, each of those segments has a slope of 0 because they're all horizontal lines. And so our acceleration time graph would be a flat line at 0. Okay. So when I post this on Canvas, I'll go ahead and try to figure out why the answer did not show up on here like it was supposed to. So check back on Canvas if you want to see the actual graphs to check your work. I'll have that up later today for you. Okay, so I do want to give you just a quick minute to look through some of these review questions, because again, these would be the types of questions that you'd see on homework or quizzes, potentially tests. So I'm going to stop the recording and give you guys a few minutes to think through these questions, and then we'll come back and look through the answers together. Okay, so grab a piece of paper, jot down your answers, and then we'll come back together in a few minutes and talk about it. All right, so that might not have been enough time to think through all of them for all of you, But hopefully this helps get your brain thinking about what types of questions might be asked about a graph like this. Now, there was a very compelling question asked in the chat that I want to make sure that we address as well. So that question is, what would the instantaneous velocity or speed be at t equals 5 and t equals 14 seconds? Okay, so you can see at those points in the graph, we're going from a negative slope to a positive slope. Now, in real life, we can't just instantaneously change direction, right? From going in a negative position to a positive position, like we can't just do that. So this type of graph is
Not if you don't try hard enough.
that's true. Not with that attitude. Right. So this graph might not be the most realistic. What we would actually see is more of a curve here at these sort of junction points. And that would show us that at that particular instance, so t equals 5, t equals 14, when we're changing direction, the instantaneous velocity would be 0, right, at those particular instants. Now, we can't really take a slope of a point on a graph, but just thinking through, like, conceptually what would be happening there, we would have an instantaneous velocity of 0. That's a great question. Okay. So let's think through some of these other questions together. Number 1, at what time or times was the particle at rest? Anytime the position is a flat line, that means the position is not changing. So from 0 to 2 seconds, the position is a constant 0 meters. From 7 to 12 seconds, we're at a position of 2 meters. From 16 to 18, we're at a position of -2 meters. And then from 19 to 20 seconds, we're back at a position of 0. Okay, so all of those times, the particle will be at rest, not moving, because that position is not changing. Number 2, when was the particle moving in a positive direction or in a negative direction? So in a positive direction, that would be when the position is increasing towards the positive axis. So from 5 to 7 seconds, 14 to 16 seconds, 18 to 19 seconds. And then vice versa, when is it moving in a negative direction? That would be when the position is getting more and more negative. So that'd be from 2 to 5 seconds and 12 to 14 seconds. Number 3, what is the total distance traveled over that 20-second interval? If we add up all of those position changes, regardless of whether they're positive or negative, just thinking about how much that position changed in total, that would be 22 meters. Now, question 4, what was its net displacement over the 20-second intervals? Here, remember, displacement is a vector, so we're just concerned with where it starts versus where it ends up. And so that would be 0 meters. It's starting at a position of 0, it's ending at a position of 0, the displacement is 0, even though it traveled a total distance of 22 meters. Number 5, what is the instantaneous velocity, magnitude and direction, of the particle at t equals 4 seconds? Right, so you can see that's right before the point at 5 seconds. So we do have an actual slope that we can calculate here. The slope at this section for the entire section is -1 meters per second. Or you could say the velocity is 1 meter per second down or west or backwards, some negative direction. Right, remember in this first answer, the negative sign itself implies the direction. So the magnitude is 1, the direction is negative. Number 6, what is the
question?
Yes.
Why is it west? You said the velocity could be 1 meter per second down, west, or backward.
Yes.
Why
So remember,
west?
when we have our cardinal directions, like north, south, east, west, when that's how we're kind of defining our directions, north and east are positive directions, and south and west are negative directions. So we don't really know what this particle is actually doing, if it's like a ball being tossed or bounced around, or if it's a car driving or a person evading the police. Like we don't really know what's happening in this scenario. So we don't really know which frame of reference we're dealing with, if that makes sense.
Okay, thank you.
Yep. Okay, so number 6, what is the instantaneous speed at 13 seconds? Speed is a scalar, the direction doesn't matter. So we're just thinking about the slope's magnitude, just its value. So even though it has a slope of -4 at that section, the speed of that would be 4 meters per second, the absolute value of the velocity. Number 7, what is the particle's instantaneous speed at t = 16 seconds? So again, we're kind of changing our motion here, changing what we're doing, right? So moving from like a positive, going towards a positive direction to stopping. And so right at 16 seconds, we're going to assume that it has an instantaneous speed of 0 meters per second. Number 8, what is the average speed of the particle? Ooh, yes.
I was thinking about this for a couple of sections now, and I did derivatives back in high school,
Mhm.
but it was like with like 6 like x to the power of 4, and I would get the derivative of that. How do you get a derivative of like a single number? I know that will equal to 0, which would like kind of throw things off.
You talking about a
So
constant?
you're actually
No.
kind of asking a question based on what we'll talk about in like 5 minutes.
Okay.
So if you can hold on to that question for about 5 minutes, hopefully it will be answered in the slides.
5 minutes is a long time. I don't know about that.
I know it's tough to wait. But let's finish up these review questions and then we'll get into how we do derivatives.
Okay.
Awesome. All right, so number 8, what is the average speed over the 20-second interval? Remember, average speed is that total distance divided by the total amount of time. We calculated total distance in number 3 as 22 meters. So we divide it by that time interval of 20 seconds. We get an average speed of 1.1 meters per second. And then number 9, what is the average velocity over that whole time frame? Average velocity is displacement, or the change in position, divided by that time interval. So if our displacement is 0 meters, then our average velocity is 0 divided by 20, which is 0 meters per second. Okay, question, how do we get number 6 again? So number 6, the instantaneous speed at 13 seconds. It's in this section, right? 13 seconds would be right here, which is within this section of the graph. So we take the slope of this section, which would be -4 meters per second. And then the speed is just the magnitude of that without paying attention to the direction. So that would be 4 meters per second. Okay, so this will all be posted on Canvas later today, like I said. So you can go back through these questions and hopefully arrive at the same answers that I did. Okay. Oh, here are the graphs I was looking for. Sorry, I'm just in the wrong order. All right, so here was our graph. We're going to calculate the slope for each of these sections to get the velocities. So I broke it down into distinct sections, right? And so we can see without numbers, the basic idea of these slopes, right? So this first section has a slope of 0, so it has a velocity of 0. This one is a negative slope, so it has some negative value. This one is a big positive slope, so it has a higher positive value, etc. So this would be approximately what our velocity graph would look like. Same process for